Welcome, everyone. Thank you so much for joining us tonight for another Black and Data Week event. And we hope that you've joined other events and had a good experience. So tonight, Lauren is going to be presenting From Bottles to Business Value, Clustering and Recommender Systems with Wine Inventory. And just to introduce Lauren, so Lauren Shores is a data scientist, that loves digging into data to solve problems and uncover insights to better understand the world and make decisions. With professional experience in both supply chain and real estate, she's led multi-million-dollar projects at a Fortune 500 company, creating machine learning models and forecasting solutions that make a real impact. Lauren earned an MS in predictive analytics from Northwestern University and is passionate about mentoring and helping Black professionals in data through her work with Black Tides Data. And outside of work, you'll find her diving into personal data projects on topics like race, place, and food. And when she's not geeking out on data, she's probably exploring new cuisines, reading, watching movies, traveling, or trying something new. So with that said, I'm going to hand this over to Lauren. Thank you.
Thank you so much, Hannah, and thank you everyone that joined the call today. So, as Hannah said, tonight we'll be talking about from bottles to business value. As she mentioned, I love food. I also love wine, which is the inspiration for this project. So, just a little background. I go to a local wine shop and that I love, and I usually go in there and I'll buy in bulk. I'll usually buy at least 6 bottles at a time, just kind of stock up. But I don't know a lot about wine. I just know what I like. And so I was thinking, wouldn't it be amazing if there was some application, something where I could just put in a wine that I know I like and just get more recommendations so I don't have to be cruising the aisles, things that I probably would like based off of what I know I already like. And so that was kind of the motivation for me digging into this project. Now, today I am going to utilize data science to understand wine inventory, not just for my own selfish purposes, but this can be expanded on to better serve customers. And so, what we're going to walk through today is how to create a simple, very simple recommendation system based solely on information about the wine, and we'll also talk about clustering, which isn't necessary per se to build a recommendation system, but it's something that is very valuable in a business setting and can hold some value in a setting like this for product or customers. And so I thought it would be nice to combine the two things together. So talking a little bit about business, the business value of it, like I said, instead of just looking at it from my selfish point of view of wanting better recommendations for myself of what I should pick out. If you think about the value of being able to recommend a product to a customer and be able to understand the synergies between products by grouping them together, that can be very valuable for a business. So it can improve product discovery, which is mainly what we're talking about for customers. Obviously, if you are given things that you like, you're going to buy more. Um, it can help drive decisions about inventory planning and placement in the store. So let's say we built a clustering system and now we know exactly what type of red wines are similar to each other. We may use this sort of information to cross sell, upsell. We might place those bottles next to each other in the store so that people can be in the same vicinity when they're looking for what to buy, the same vicinity of similar products. Um, this particular project doesn't address this, but if paired with sales data, we can really assist with customer segmentation if we were to do this clustering exercise for our products, and it could really help with targeted marketing. And the last kind of business value that could come from an exercise like this is actually helping employees of the store to learn the inventory quickly. If you get hired as a young person working in a wine shop and you don't know a lot about wines, and people come in and ask and you don't know, having a tool like this where the employees could actually easily look up this information, easily find products that are similar to each other, could just make the store look better, equipped to cater to their customers, and again help in making those sales. So, like I said, just I wanted to bring in the flip side of this, because as data scientists and data analysts, it's all fun and good to be able to harness these algorithms and do these cool things, but at the end of the day, like, there needs to be a value behind it. And so yeah. um, Also, I didn't say this before, but feel free to stop me if you have any questions. Feel free to put them in the chat or even unmute yourself at any point. I welcome questions. So here's the agenda. We're going to walk through the data I used. We're going to talk about clustering. We're going to talk about the results I got from the clustering exercise and some of the challenges faced when using real world data. Conclusions, and then we'll move into the recommendation part of this, which is driven mainly by cosine similarity. So we'll talk about that a bit, and we'll talk about opportunities for improvement. Okay. So the data, as I've mentioned, this is all from just a store that's close to my house, a wine shop. They have a website. I went on their site and scraped the inventory for all of their wines. I came up with about 911 rows. Um, the data were incomplete. So they had data ranging from obviously the title of the wine, price, description, the year, vintage, is it red, white, rosé, whatever the color, variety, producer, region, and style. And as you can see here, I kind of listed how much of that data was not missing for each of those features. When you get any data, you're rarely going to be able to just plug and play. You got to do some cleaning and some feature engineering. Obviously, since I mentioned missing features as a problem, I did my best to extract information for some of the features through other features. So, for example, a title of a wine might be um, Red Paso Robles, um Sonoma wine, right? So that title actually has a 2023. So that title actually has information about color, vintage, where it's from. So that is one of the exercises that I did do, was looking into the more complete roles, such as title, and extrapolating information for some of the missing features through that. Um, Imputed missing color categories from type of wine. I know Merlots are red, so if color is missing, but I know the type of wine is Merlot, I filled it in, so that sort of thing. Um, Extracting adjectives. So a lot of this clustering exercise is based off of the text description, because ultimately we want our clusters to mean something. We don't want just to say we have some groups and they don't they're not telling us anything. Like, we can't say anything in particular about the group. So using the descriptions or adjectives from the descriptions and noun phrases like, oh, this wine has hints of berry or notes of plum. We're using those type of words in the descriptions to kind of drive this clustering exercise. And obviously, you're working with categorical data. So, anytime you're running that through machine learning models, you're going to have to do some type of manipulation to convert that text into numbers, whether it be, vectorizing the descriptions or one hot encoding categories. Okay, so clustering approach. As I mentioned before, we're only dealing with records that have a description because we want to be able to say something about these clusters. And that's the easiest way is if we have them driven by that description. So we're only dealing with records that have a description. I mentioned creating the features with the adjectives and also vectorizing the descriptions. So when I say vectorizing the descriptions, if you are not familiar with a little bit of NLP, natural language processing methods, essentially it would be very difficult to run plain text through any type of machine learning model. You need to convert that to numbers, and more specifically number vectors. And so earlier natural language processing techniques like word2vec, even bag of words, where you're literally just like counting words and creating a vector out of the list of words that pop up in a particular description. These are all methods that can be used to convert text into numbers. And so for this particular project, I tried a bunch of methods, but the one that I'm presenting or landing on here with presenting results is transformer models. And if you're not aware, transformers are behind LLMs. So they're a good thing to kind of start to get familiar with. Combining encoded categorical features and description features. So we have, as I mentioned, features such as the color of the wine, the variety of the wine. Is it a Merlot? Is it a Cabernet? Is it a Malbec? Which again, those categorical features need to be encoded to numbers as well, right? Well, ultimately, the task was to bring all of these features together, not just the description, but color, variety, etc., into a matrix that could be consumed by a machine learning algorithm. Another thing that I did in this approach is to remove outliers, which again, a lot of this project was trial and error. So I started out not doing that. And I got very poor results with clustering. And by poor results, it just basically means that you're getting groups that don't really mean anything, like they don't have any strong similarities. There's no strong reason why these things are grouped together. And I'll talk about outliers a little bit more and why removing them was important to this clustering method. And choosing and evaluating the number of clusters. So I mentioned this before, I believe. The algorithm that I used was k-means clustering. There are other methods, machine learning methods, to create these groups and to cluster your data. But this particular one requires that you tell the algorithm how many groups you want in advance, which can be very hard, right? Like if I just gave you a set of data and said, this is a data set of wine of about 1,000 different wines, make some groups out of them, and you have to just come up with, oh, okay, I think I need 5 groups or whatever. That could be very, very hard, which can be a challenge for k-means clustering and can really affect your outputs. But there are methods like elbow method, which uses error metrics to kind of figure out what the right number of clusters are or groups. So that was all a part of this approach. Okay, so once we get the clusters, it's time to try to start to understand them. So some of the methods that I use to try to understand the clusters was to look at what are the top categories for our categorical columns. So for example, if I am having 4 clusters and I know that, for example, color is one of my categorical columns that's driving this cluster, I want to know out of the 4 clusters, which one of these categories, let's say it's red or is it rosé or white, is the category that occurs the most. So that's a good way to kind of understand or describe what's happening in the cluster, especially if it's a strong majority for that cluster. Most common words and bigrams in the descriptor. So it's the same kind of idea. You have 4 clusters. What words show up the most in cluster 1 versus cluster 2? That can give us an idea about what these clusters actually mean, what's important to them. Highest TF-IDF scoring words. It's kind of similar. So I didn't explain this before, and again, this is another natural language processing method, but essentially it's very similar to what is the most frequently occurring word. But TF-IDF is a method that actually downweights words that occur throughout every description. So for example, we have a description for each of our 900 wines, or 400 since we only use wines with a description. We have a description, and every description, or the majority of the descriptions, have the word wine. So if we were to just use plain frequency of words, wine would seem like a very important word. But the truth is that wine occurs in every description. That word occurs in every description. So it's actually not a very important word. And so TF-IDF is a good method to use when you want to know what kind of the important words are in your body of words. So after doing these methods to understand, we also did a couple visualizations looking at the clusters, and also something called a silhouette plot, which I'll talk a bit more about. I'm going to pause because I feel like I've said a lot, just in case you guys have any questions thus far. Any questions? Anything that needs any clarity? Or like just a show of hands too, you guys can use the little, I think there's a reaction thing. Are you guys familiar with, or how many of you guys are familiar with natural language processing methods like TF-IDF and, word vectors, word embeddings? Show of hands. Choice, that's choice. Cool. It's fine if you don't. Like, that's what we're here for, to learn. So it's just good for me to know. Okay. Some notes about clustering. So as I mentioned before, k-means clustering is the method that I used here. You do have to choose how many groups at the beginning before you start doing anything. And also, I'm going to explain a little bit about how it works because it can be really finicky. So k-means clustering is a distance-based algorithm where, let's say you have your data points, you know, on a, in a graph in a space. And what k-means will do is that it will initialize at random um, some data points in the space of your data. And all it's trying to do is it is looking at what data, like in your actual data set, is around these data points. And it will calculate the distances from your initialized centroids, that's what we'll call them, your initialized centroids. It calculates the distance between each point that's in your data set. And it calculates the closest centroid to your data points, and that's how it decides which cluster it goes into. And it also iteratively changes, like um, because your centroid will change as you put more data points into that cluster. Your centroid will always change to kind of be more so in the middle of all the points assigned to that cluster. So why do I say that? Because, you know, how many clusters you choose matters because, like I said, that's going to be how many centroids you have and thus how many, where your points are going to get assigned, like your data points. Outliers are going to matter. So if in the space of your data, you happen to have some point that's way out there and it gets assigned to a cluster, well, now when the centroid is recalculated, it's going to pull the centroid out towards that outlier, which means that it's going to affect everything else as far as distances to the nearest centroid. So outliers can really screw things up for this algorithm. Um, we in this data set, all of our features are categorical. So we're talking either vectorized descriptions or one hot encoded categories, which is, either, is it red? Is it a red wine? Yes or no, 0 or 1. So that means that our data can get very wide. We'll have a lot of features with potentially a lot of zeros. So that can be an issue as well. Um, Using variables that are highly correlated can also screw up k-means. So you have to be careful. You can't just say, okay, I have all of these features in the data set, and so I'll just use all of them. If there are features that are kind of doing the same thing, it probably makes sense to take some of them out. You're going to reduce the dimensionality of your data set, which is going to be better anyway. Um, so yeah, that is a challenge. And then, um, yeah, I talked about random initialization of the cluster. So these are all things that you want to think about when you are using the k-means algorithm to make your groups. Now, I'm going to jump into results. I did a lot of experimentation as far as which variables I put into the algorithm, what method did I use to create word vectors or embeddings for my descriptions. Um, yeah, so I did a lot of experimentation there to see what came up with the best results, and also outlier removal. Like over an iterative process, I realized, yeah, taking out outliers yielded a lot better results. And so what I'm showing you here is the result of using 4 clusters, which again was selected using the elbow method, which, like I said, essentially is looking at reducing the sum of square error, how many clusters or how many groups reduces the error by the biggest bump. That's essentially what the elbow method does. And it came out to be 4 clusters for this particular data set. And so here, the only variables that I'm using are color, variety, and the description embeddings. To the left, you'll see a visualization of the clusters using PCA, principal component analysis, which is a way to reduce the dimensionality of the data. Like I said, we have vectors that are huge because we're using text data, so there's no way to graph that on a 2-axis plot, right? So that's where this method comes in handy. The interesting thing about grouping these first 2 principal components is that they are colors. Each color is a cluster. They are separate, but we do see, for example, green and yellow. Actually, all of them have like a big space. Like there's almost groups within a group. So green has 2 groups, yellow kind of has 2 separate groups, blue has like a little outlier thing going. And I'll talk about that a little bit more. But so here we kind of see what the first 2 components are doing. If you look at the bottom plot, I graphed, sorry, the first 4 principal components. And the reason why I did this, of course, if you just look at the axis for component 1 and component 2, you'll see the exact same graph that is up in the upper left hand corner. But I like this plot because basically when you plot the other components, you kind of see from a different angle what the data is doing. And also this outputs percentages of the components. So what we see about this data set is that the upper left-hand plot of the first 2 components make up about 35% of the data. So what does that mean? It makes up about 35% of the variability of the data. So 35% of what's happening in the data, the variability can be explained by these components. So that's something worth thinking about, especially because we're going to be trying to use this to say something about groups. I mean, if only 5% of the data was explained in the first 2 components, it probably wouldn't even be worth talking about, right? So that is an important thing. And then the last thing with these visual results of the wine is the silhouette scores. So this silhouette score is about 0.3 almost. The upper right hand plot shows you a plot of the silhouette scores for each of the 4 clusters. Each color is a different cluster. And we see here that some clusters perform better than others. So the higher the silhouette score, the better the performance. So we see that cluster 2 here, their silhouette scores range from like probably 0.2 up to 0.5. Whereas, the green one is a little lower, but it's one of the biggest clusters. So the width of the cluster is like how many of the data points fall into that cluster. I will mention here that having a silhouette score or average silhouette score, because that 0.29 is an average of all these scores together. Having a score at that level is it's not amazing. It's fine in the sense that real world data is very tough to cluster, and so it basically means that these clusters aren't super stable or super structured, but they can be helpful in telling us something. So we don't have to throw them out with a score of 0.30. Continuing our results here, I have added in a couple of the charts. So when I talked about the approach, I mentioned that we wanted to look at the most common of our categorical variables. So, right, we have here the most common variety, the most common color. And we can see that, one of we can see that for each of these different four clusters, they actually break out pretty nicely with having a most common color. So automatically I'm thinking, okay, these clusters may be driven by color more than anything. So if I pick a particular cluster, it's more likely that, or cluster two is more likely that it'll be a red. Also, I included here the percent of the data, which tracks pretty nicely to actually the percent breakout of the colors of the wines. So again, just providing evidence of these clusters being heavily driven by color. So yeah, this exercise of grouping, of using k-means to group all of the wines, suggests grouping wines by color is something that k-means can can definitely do. Now, how helpful is this particular type of grouping in the real world? Probably not much, because we know the colors already. We can go in the store and group our colors without without necessarily needing k-means to do that, because it's on the bottle. But I will say one of the helpful things is if you didn't know anything about wine, and you have these four clusters, we are getting the sense that they're driven by color. If we dive deeper into, let's say, our top words for our TF-IDF, or even our top words just based off of frequency of words, now we are starting to get some descriptions to tied with these colors. So cluster two, we know is driven by red. We see the word grilled, we see rich, hearty, dark. For white, cluster zero is white. We see vibrant, refreshing, um, light. I mean, I don't know if you guys drink wine. Obviously, like, these are words I probably would know otherwise, because I do drink wine. But if you didn't know that, a white or a rosé is going to give you, floral, or sparkling, an exercise like this, I think, even if you determine, okay, like, these clusters are driven by color, having that data behind it with these descriptors can help give you language to talk about these clusters with more than just, oh, that, we're breaking these lines out by, the color. So I'm going to pause again before I go into the next part. The next part that I'm talking about is actually doing the same exercise, but only for red wines, because, like I said, it's easy to group wines by color, without an algorithm. But what can we do when we're trying to group wines of the same color? That's what we'll be talking about next. So I'm gonna pause here. Any questions? By a show of hands, has any of you used k-means clustering before? Feel free to use your emoji hands. Hannah has, great. All right, thanks. I hope you guys are, taken away, because, like I said, it is an algorithm that is very useful in industry, particularly um, in business. Excuse me. Okay, so jumping into clustering the red wines. Now, this one is interesting. Obviously, there are less rows of data, only a little bit over 200. We have 9 clusters instead of just the 4 that we have when we were using the entire descriptive data set. We used less variables, because obviously we don't need to use color. because all of them are wine. I mean red, sorry. So we used variety, varietal, and the description embeddings as our features in this algorithm. And we see off the jump that our silhouette score, which is kind of the main score that we use to assess the goodness of clusters, is at about 0.45, which is what, 0.15 more than the other algorithm when we were doing it for all of the wines together. So just taking a look at these graphs a little bit, these plots, looking at the upper left hand side where we look at our first two principal components, uh, there are 9 clusters. We see straight off that 4 of them are very separate, or at least there are 4 very separate groups. And 4 of them are separate clusters, and then the one in the middle is kind of a bunch of clusters just right on top of each other. So right away, that's very interesting to me. That's telling me that red wines have at least 3 very separate type of things going on. We don't know what they are yet, and then a bunch of them are the other clusters are kind of very similar, at least as explained by the first 2 components. We see that if we go to the bottom plot, again, looking at the first 2 principal components, um, they explain about 30% of the variability in the data, which I think is about the same as the other one we did. I think it was 30% as well. And then if we go over to the upper right hand side and look at the silhouette plot for that, this one is a bit more interesting. So even though overall, on average, we have a higher silhouette score with most of the data points falling to the right of this dotted red line, which is our average, one of our clusters actually has a very low score and even has a negative silhouette score, which is really bad. It just means these points are like totally out of it, not doing their thing as far as being explained by these clusters. This yellow number 7 um, cluster, sorry, group, if we go over here, we see it's obvious that it's one of those that's in the center here. And so any information that we would glean when we dive into some of the other things that we're doing to make sense of the clusters, we'd have to take a grain of salt when talking about cluster 7. Okay, so I talked about this. We see 3 distinct groups when we plot our PCA. The biggest, those 3 groups make up about 52% of the data. So we know offhand that about half of the data in red wines can be distinctly separated and grouped. I talked about the 30% of variability explained in the first 2 principal components. Clusters seem to be driven by variety. I believe I have a plot to show why I think that. We'll get to that. And I mentioned the silhouette score. So this is the breakdown of TF-IDF and the most common words in our variables. And so this is why I say clusters seem to be driven by variety. Obviously, variety was the only categorical variable that we used in this algorithm, so it makes sense that it would be a major driver. But yeah, we can see that our groups kind of strongly hold to the type of wine, whether it be a cab or a blend or a Malbec. And again, going over to our top words by TF-IDF. Again, I think this is helpful because it's giving us some language um, to talk about our different clusters.
Hi,
Now,
Lauren. We have a question from Dr. Joyce. Go ahead, Dr. Joyce.
Hi, Lauren. My question is, so these numbers that are coming up and the actual clustering, how do you think they compare to you as a real live connoisseur? Do you agree, do you agree with what they're saying? Are they coming in with what you kind of expected? Not, not necessarily down to the percentage, but that they're actually being clustered the way you as a connoisseur know them to be. What's the correlation between what they're actually saying and what you know and feel, and would you make the same recommendations that the K-means algorithm is making, knowing what you know?
yeah, I would say, so again, for the one where we did it for all of the wines, I think the K-means did a great job. Like, yes, it's very simplistic because it is driven by color, but the fact that when I went back and checked and the colors were in the right group, that tells me K-means is doing its job as far as like honing in on that. And then also with the one that's overall all of the wines, when I look at the descriptions, again, the top TF-IDF words fall into place about what I know about different types of wine. I know that white wines tend to be more refreshing, more light. I know that red wines go good with grilled meat or maybe cheese. All words that showed up as top TF-IDF words or even top words. And so I would say that particularly for that grouping, um, the clusters make a lot of sense. For
So
this,
were those words were those words part of your scraping, like cheese and chocolate and red
yeah,
meats and stuff like that?
yeah. So I can show it later if you guys want to look at code, but literally in the description, the way this wine shop does it, they write their own descriptions for all of their wine. Well, not all because there's missing data, but for the ones that they bother to write descriptions for, they'll say something like, this wine is rich and refreshing with notes of plum and berries, goes great with grilled meat, pasta, hearty cheeses. Like it'll have a full like a full description to it, right? And so so yeah, so those are the type of words that do show up because they write those kind of descriptions.
Okay, thank you.
You're welcome. um any other questions? Going along with what Dr. Joyce asked, so for the red wines, it's a little more difficult, right? Because as far as like, do these groupings make sense? As far as like what I know as someone who likes wine versus what this algorithm is telling me should be the descriptions of these clusters. I mean, if you look at these TF-IDFs, a lot of the clusters have very similar words, right? Grilled pops up a lot. Um, what maybe dark pops up a lot, which makes sense. It's a red wine. It's going to be dark. Well, there are some light ones, but dark pops up a lot. So there's things like that where you're getting descriptor words, but because there's such a fine point to this, these descriptions may not be doing an amazing job of uh, telling you something that makes this group unique from that group. But I think here, if you do take it more for the varietal aspect, meaning a Merlot versus a Cab, if you look at the groups from that standpoint, and if you know a little bit about wine, so like if a Merlot and a red blend pop up in the same group, well, a Merlot is a blend. Like yeah, a Merlot is a blend, so that makes sense. So I think, and you'll hear this in business too, like it's it's good to look at this data and see what the algorithms are saying, but it's really good if you have someone with some domain knowledge there next to you, or if you have that knowledge to be able to make sense of it. Okay, so that is what I'm going to talk about for clustering. I'm going to move into recommenders. I know we're just have a little bit more time. I don't know if you guys want to see code, but we can after this if you want. So a little bit about recommenders. We're all familiar with them, right? Like we don't even think twice about it. Netflix, Amazon, all of these things are constantly feeding us recommendations of things we should be looking at or buying. Spotify, listening to. A lot of these recommender systems that we use, there's two main types of ways that organizations make recommendations. A, through collaborative filtering. So they are harnessing the power of your activity with their product, your ratings, and other people's activity and ratings to thus recommend something to you or suggest something to you that may be similar based off of your behavior and other people's behavior. That's collaborative based filtering. We're not doing that because we don't know anything about anybody, right? We only know about our product. And so we are using a purely content-based filtering method because we have no information about customers, their purchasing habits, or anything like that. And so basically, all of the things that we did before with creating our one-hot encoded categorical variables, creating our vectorizations of our word descriptions, all of that is now the framework or foundation for moving ahead and making a recommendation. We've already done the legwork for this. So all we really need to do now is take our matrix of features that we've created for this other exercise and calculate cosine similarity. Again, it's all about distance with these algorithms. Cosine similarity is basically finding minimal distance between features based off of cosine. I'm not going to get into linear algebra, but that's what it's doing. And yeah, so you can use not any, but there are packages or in Python that you can use to calculate a matrix of cosine similarity so that if for your data set for each row, you would have a similarity score between every other product. And once you have that, well, you could say, I just want to pick the top. So I don't want to get overwhelmed with recommendations. So I'll pick the top 5 cosine similar products to this one product that I'm interested in. And that is the basis for a recommendation. Now, if you wanted to make your recommendations more useful, I'm not rich. I care about the price of the wine. So maybe you throw something like a price filter into your recommender system so that, I'm getting the top 5 wines that are under $25, just to, give you recommendations that your users will be more interested in. This next slide, and I've already kind of started talking about it, it's just opportunities to expand this project, to make it better, to make it more useful. Here we focused on clustering, using k-mean clusters to get our groups. But we had basically half of the data that we couldn't do that for because it didn't have a description. One thing that people tend to do in industry, and you could do, is to use k-means clustering to create groups, which, if I haven't mentioned it before, is an unsupervised learning method. And you could then use a supervised learning method, a decision tree, something like that, to um, predict class labels that you came up with from your clustering algorithm. Train a model to do that, and then it would be extensible to other data that you weren't able to group before. So that's one way to expand this. Different clustering methods. So k-means is not the only method out there, and it's not always the most appropriate. I've already mentioned some of the challenges with it, and there's other methodologies that have trade-offs for what it does. HDB scan is one that could be a good alternative. I didn't get a chance to use it in this project, but it definitely crossed my mind, and given more time and energy, could be something I would try. And then augment the recommender search. So the part of me that wants to use this to actually, get better wine recommendations for myself, says that, I could make this a lot better if a user could just input a string of text rather than specifically inputting the title of a wine. And based off of that string, let's say I'm looking for a dry red wine, it would use these algorithms behind it. It would use cosine similarity. It would use what it knows about the features that I've already built and give me recommendations based off of that, instead of being so specific to, like I said, having to input a specific product and then get similar products. So yeah, that is that is the end of the presentation. As I said, I do have code. I'm looking at the time now. We only have 5 minutes, so I'm not gonna dive into the code, but sorry. I will be posting it on GitHub if you are interested. The good thing about me is that I tend to really organize the notebooks that I use to do this analysis. So it's all sectioned out. If you're interested in that, when we get it posted, it'll be very easy to follow the code. Any questions or concerns, comments? Who likes wine here? Show of hands. Hannah. What kind of wine do you like, Hannah? Are you a white or red?
I don't know actually. I think maybe white wine.
Yeah. Do you think you'd use something like this? If I get it off the ground, I make an app.
A lot of people would use something like this. I think maybe even the store that would love something like this as well. So definitely a project worth exploring.
Yeah, for sure. Any other questions? Let me look at. Okay. Well, if that is it, never had a drink. Oh, Dr. Joyce.
No, honestly, I haven't. But
No.
no. And every time they go to do my background investigation and to do my polygraph, and they ask me about drinking and smoking, and I say no, and they were like, they don't come right out and say it, but it's like, you old as dirt. How could you never have had a drink or never smoked marijuana? And said, I just never have. I said, I have uncles and brothers. They got me covered. And now I got nieces and great nieces. They got me covered.
Well, they say red wine is good for the heart, like a little in moderation, obviously. So maybe
Yeah, that's what I've heard. That's what I've heard. But I know that once I like something, I just become addicted to it, like poppycock and apple juice and cranberry juice. I would be like an alcoholic in a matter of a week.
Okay, so yeah, maybe you should just
Yes. Yeah. Yeah, my brother's in the background. He was like, "No, you don't need to start drinking at this late age."
That's funny.
Yeah. Yeah.
Lauren,
This was really good. My niece used to work for the place in South Carolina that does all of the liquor and wine, like the ABC, the Alcohol and Beverage Commission. She worked for them. So she knows a lot about wines and stuff like that. And she has all kinds of wines because before a wine can or liquor can be distributed in South Carolina, it has to go through the ABC and it has to go through Southern Glacier and all of that before it can be sold in a hotel or in the grocery store anyway. So she knows a lot about wines and they give them a lot. You know, they trying to push their product.
Mhm. Cool.
Ashley had texted him a while back.
Well,
all right.
thank you.
But as soon as I start, I'll let you know.
Okay, don't blame it on me though.
If I have to be in Chicago in the wintertime, I'll be drinking and smoking.
Okay, I think unless anyone has any other questions, thank you so much, Lauren, for the amazing presentation. I learned a lot about K-means clustering and other classification algorithms. So this is really fun. And for everyone who joined, thank you so much for joining. If you could take a minute to please do our survey, this would be really helpful for us for future Black and Data Week programming. But thank you again so much, and thank you to Lauren.
Thanks, everybody.
Bye,
Bye.
everyone. Good night.
All right, thank you. Good night.